Welcome to This Explainer. If you've ever wondered what actually separates a slow, clunky program from lightning-fast software that scales effortlessly to millions of users, well, you are in the exact right place. We're going to embark on the ultimate quest for efficiency by unpacking the fundamental building blocks of computer science. And we're going to do it in a way that's visual, structured, and most importantly, immediately actionable. Let's just jump right in.
All right, here's a quick mental roadmap of what we're covering today. First, the backbone of software. Then, measuring efficiency with big O, followed by foundations like arrays and strings. Next, the magic of hash tables, flexible memory with linked lists, and finally, stacks, queues, and trees. Section 1. The backbone of software, defining the core concepts. So, let's get our definitions straight. A data structure is simply how we organize and store data efficiently in a computer's memory. Think of it like the physical shelving in a massive warehouse. An algorithm, on the other hand, is the step-by-step set of instructions, basically the recipe used to compute, search, and manipulate that data. Think of the algorithm as the warehouse worker actually executing a specific path to retrieve your box. Together, these two concepts form the absolute backbone of scalable programming. You really can't have one without the other. Now, this perfectly illustrates the central tension of all software engineering, the eternal trade-off between time complexity, which is speed, and space complexity, which is memory. Time complexity measures how your runtime grows as your input size gets larger. Space complexity measures how your memory usage grows, stuff like stack space, heap space, and auxiliary variables. The absolute secret to software engineering is that optimizing one almost always forces a trade-off with the other. If you want blazing fast speed, you're often going to have to sacrifice and consume a lot more memory to cache those results. Section 2. Measuring efficiency. Big O, the universal framework.
Big O notation is brilliant because it makes efficiency visually clear. Look down at the very bottom. We have that excellent flat blue line of O of 1 or constant time. This means no matter how insanely massive your input size gets, the operation takes the exact same amount of time. Moving up the chart, we scale through logarithmic and linear times like O of n log n in the orange zone, and then at the very top we have the absolute terrible vertical red spike of O of 2 to the n, which represents exponential time. This horrific performance will literally crash your system as your input grows, so you want to use this chart as your primary map for evaluating absolutely every structure.
Moving on to Section 3. Foundations, arrays, and strings, the simplest structures. Arrays are incredible because they give us lightning-fast O of 1 random access. Why? Well, because an array is a fixed-sized, contiguous block of memory. The computer knows exactly where every single item sits. If you want index 4, boom, you are there instantly. But because those memory blocks are packed so tightly together, searching for a specific value or inserting new data right in the middle forces an O of n operation. You literally have to scan through or shift all the subsequent elements over just to make room. Dynamic arrays, like Python lists, try to fix this by automatically doubling their size when they get full, but they still suffer from that linear O of n search time. And that is exactly why we've got to use them wisely. Now, strings are essentially just sequences of characters that share those exact same underlying array mechanics. In a lot of languages, they're immutable, meaning you literally cannot change them in place. You have to create a whole new string from scratch. Because they share array properties, retrieving a substring or concatenating takes O(n) time. So to boost their operational speed without eating up excessive space complexity, engineers rely on clever little algorithmic tricks, like creating a sliding window or using two pointers to traverse the string sequentially from both ends at once.
Section 4. The magic of hash tables, solving the lookup bottleneck.
So how do we get around that search bottleneck? We need a totally different paradigm, and that brings us to the hash table, which stores key-value pairs. Here's the flow. Step 1, you provide a key, let's say the string name. Step 2, you run that key through a mathematical hash function. Step 3, that math assigns the key directly to a specific bucket index in memory. And Step 4, you instantly retrieve or store your associated value, like Alice. This entirely bypasses the need to scan through your data. It delivers your value in an amazing O(1) average time. Now, if two keys happen to mathematically map to the exact same bucket, which we call a collision, the hash table just handles it by chaining a tiny linked list right there in the bucket or by probing for the next open slot. Okay, the really crucial point here is this somewhat surprising number, 0.75. This is the load factor threshold. As you pack more and more data into your hash table, collisions become pretty much inevitable. When the number of items reaches roughly 75% of your available capacity, a hash table has to dynamically resize itself, usually doubling its memory footprint, just to avoid continuous data collisions. By sacrificing this extra memory space, it guarantees that you maintain that blazing O of 1 lookup speed. Space trades for time, right there in action.
Section 5. Flexible memory. Linked lists. Breaking out of rigid blocks.
So, what if we need dynamic memory but we don't want to pre-allocate massive contiguous blocks? Linked lists solve this by literally chaining data together with directional pointers. A node can live anywhere in your computer's memory as long as it points to the address of the next node. But remember our ongoing trade-off motif? Look at the singly linked list on the left. You gain absolute O1 instant insertions at the head, but you completely lose the ability to randomly access an index. To find the 10th item, you've got to hop through 9 pointers, meaning search is O of n. Now look over at the doubly linked list on the right. It adds a previous pointer. This elegantly gives you O1 bidirectional traversal. You can walk forwards and backwards effortlessly, but it costs you exactly double the memory overhead for all those extra pointers.
Section 6. Stacks, queues, and trees. The specialized toolbox.
First up in the toolbox, stacks. Stacks enforce a highly strict LIFO rule, last in, first out. Just picture a physical stack of plates in a cafeteria. The very last plate you push onto the top is the absolute first one you pop off. This structure perfectly mirrors how your browser's back button operates, how balanced parentheses are validated in code, or how the undo function works in your word processor. Everything happens right at the top in constant O of 1 time.
Queues, on the other hand, flip the script entirely to FIFO, first in, first out. This works exactly like a real-world checkout line at the grocery store. The first person to enter the line at the back is the first person served at the front. Whenever you click Print on a document, or when an operating system handles background task scheduling, it's using a queue to maintain absolute fairness and chronological order. And again, operations here are an incredibly efficient O of 1.
Lastly, we break out of straight-line data and into hierarchical logic with trees. You've got a root node at the very top and leaves with no children branching down to the bottom. The absolute magic of a well-balanced tree, like a binary search tree, is that at every single node, you make a decision that cuts your remaining possibilities entirely in half. You can actually measure their search efficiency simply by tracing the path height. Because you are constantly dividing the search space, a balanced tree operates in a beautifully fast O of log n time. It's vastly faster than scanning an array, all while keeping complex hierarchical data perfectly structured. But, quick warning here, if your tree becomes heavily skewed, where every node only has one child, it degenerates right back into a slow O of n linked list.
So there you have it. We've charted the map from the rigid speed of arrays to the mathematical magic of hash tables, all the way to the hierarchical logic of trees. Every data structure we've explored today is simply a tool, and each one comes with a very specific, mathematically proven cost and benefit in our eternal tug-of-war between time and memory. So, looking at the engineering problem sitting in front of you today, the ultimate question is which structure will you choose for your next algorithmic trade-off? Thanks for hanging out for this explainer. Keep optimizing, keep building, and we'll see you in the next one.